Good? Alright. So the last class that we had, when we covered class material, we really quickly introduced the idea of congruent right at the end of class, just to try and give you a taste of chapter 4 before we jumped into it. And then today I plan on covering chapter 4 and chapter 5. Chapter 4 is really short, and chapter 5, the author's trying to do some proofs of analysis that he's not really doing it very well, so we'll kind of just rush through that, and we won't bother doing it real well either. And then chapter 6 is when we start doing geometry like Euclid did, when we get to triangles and stuff. So for chapter 2 and chapter 3, we had these 4 undefined terms that we came across: plane, line, point, and between. And they all had axioms associated with them, right? So now we're introducing a new undefined term, congruent. And if you introduce an undefined term, how do we give undefined terms meaning? Postulates, axioms. That's how we give our undefined terms meaning, right? We can't give them meaning through definitions. We can't define our undefined terms. So we let our postulates state properties that they have to have. So they're anything that satisfies these properties. That's what we mean by between, or that's what we mean by point, or that's what we mean by line. Right? So we're introducing this new idea of congruent, and the author takes the time to go through a conversation of how congruent is really trying to capture this idea of length. And we're capturing, if you looked ahead to chapter 5 is when we finally introduce numbers. Yet chapter 4 is when we're talking about congruent and something that's meant to capture the idea of length without numbers. So how can we talk about length without numbers? Right? So how tall is this classroom? Do you know? No. Neither do I. How tall am I? Do you know? No. Is this classroom taller than me? Yeah. So we're still able to make some statements about this classroom is taller than me and I am shorter than it without knowing the precise number that represents my height and the precise number that represents the height of this thing. So you don't need numbers to talk about lengths relative to other lengths, right? So that's kind of the conversation that the author starts out chapter 4 with, and then he introduces this idea of congruent, which he says, for now you can think about as the length of something, and he puts the quotation marks around it, I think. So we've got this undefined term congruent introduced to us, and we get 3 postulates that come along with the idea of congruent. So let's go over each of the postulates and make sure that they make sense to us. So the first postulate with congruent is, given 2 points, A, B, on some line L, and 1 point, A prime, on some other line L prime, there exist 2 unique points on either side of A prime, we'll call them B prime and C prime, such that AB is congruent to A prime B prime, and AB is congruent to A prime C prime. So what's he saying? He's saying, look, if I'm given these 2 points on this line, and I'm given some random point on another line, I can go this way on this line and mark a point so that this is congruent to this, and I can go this way on this line and mark some points so that this is congruent to this. Does that make sense? Mm-hmm. So that's what the first postulate is saying. Good?
Yep.
All right. Second postulate. Second postulate, in short, says congruence is an equivalence relation. And some of you understand that, some of you don't, so we'll go over the properties of a congruence relation. What it means for something to be a congruence relation is it has this property of reflexive, symmetric, and transitive.
You mean equivalence relation?
Oh, what did I say?
Congruence.
Equivalence relation,
Yeah.
yes. When we say that something's an equivalence relation, we mean it's reflexive, symmetric, and transitive. So reflexive means it's related to itself. The relation we're talking about is congruence, so AB is related to itself, or since we're talking about the relation congruence, AB is congruent to AB. I changed the order of those BA, that wasn't meant to happen. Because AB and BA, we can write that either way, that doesn't change anything. So 1, a line segment is congruent to itself. Or in other words, it's reflexive. 2, if AB is congruent to CD, then CD is congruent to AB. This is called symmetric. If you can flip the relation around, we say it's symmetric. And then finally, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. This is called transitive. And to help establish your intuition for some equivalence relations and some non-equivalence relations from last class, we talked about the relation less than. Is less than an equivalence relation? Right. Right out the door, we can throw it away. Is AB less than AB? Well, we're talking about line segments here. Let's pretend we're talking about the numbers. Is 9 less than 9? No, so it's not that. If 9 is less than 10, is 10 less than 9? No, it's not that. If 9 is less than 10 and 10 is less than 11, is 9 less than 11? Yeah, so the only one of these properties it had is it was transitive.
It has to be all three.
Yeah, but it has to be all three to be an equivalence relation. So now let's look at an example of an equivalence relation. Have the same parents as. Do I have the same parents as myself? Yes, so that's reflexive. If I have the same parents as you, do you have the same parents as me?
Yes.
Yes, so it's symmetric. And then finally transitive. If I have the same parents as you and you have the same parents as Jane, do I have the same parents as Jane? Yes, so it's transitive. So there's some intuition for what we mean by a congruence relation and what we don't mean by a congruence relation. And so the second postulate is just saying that, not congruence, I keep saying that, equivalence relation.
I think it's just the end.
So the second postulate is just saying congruence is an equivalence relation. I'm sure I'm going to screw that up when I say it again. All right, and then finally the last postulate. The last postulate, for those of you who remember Euclid's postulates, is very similar to one of Euclid's postulates. Well, let's go over it and then I'll explain that. So this says, if B is between A and C on some line L, and B prime is between A prime and C prime on some line L prime, then if, we're going to handle two cases, if AB is congruent to A prime B prime, and BC is congruent to B prime C prime, then the whole thing is congruent to the whole thing. So if this piece is congruent to this piece, and this piece is congruent to this piece, then the whole thing is congruent to the whole thing. The way Euclid said that is equals added to equals are equal. Right? And then the second postulate, I put a star next to it because it doesn't have to be a postulate. We can actually prove this from the other stuff we were given. But the author gives it to you as a postulate because it's nice. So this one tells us how to add. The second one just tells us how to subtract. This second one says, look, if AC is congruent to A prime C prime, and, which one do they use? BC is congruent to B prime C prime, then AB is congruent to A prime B prime. The way Euclid said that is if equals are subtracted from equals, the results are equal. Does that make sense? All right. So that is our three postulates that we introduced for chapter 4. Sorry, I got my pages turned here. So now with those, let's introduce a definition. And the definition that we're going to introduce is less than and greater than, I think. If you have any questions about anything that we've covered so far, just shout them out. Okay, yeah, that's what the next definition is. So the next definition, he starts out by defining, I don't know which one he does first, but it doesn't matter. So we'll define what it means for AB to be less than A prime B prime.
B prime.
B prime, thank you. All right, so what does it mean for AB to be less than A prime B prime? It means that if we have a line segment with AB, and we have some line with A prime, B prime, so what it means for AB to be less than A prime, B prime is that if we were to come down onto this line, and if we were to draw some point call it B double prime, such that AB is congruent to A prime B double prime, then B prime would be between those 2 points. Right? Does that make sense?
Yeah.
Let's say that one more time. In order for AB, oh, I did that backwards. Sorry. Well, we'll just start out with greater then, because that's the picture. Sorry, I did that backwards. So we'll say AB greater than A prime B prime. Sorry about that. So if AB is greater than A prime B prime, that means if we take AB and we go down onto this line and we draw B double prime such that AB is congruent to A prime B double prime, then B prime is between those 2 points. So what does this mean? This means that there exists B double prime such that AB is congruent to A prime B double prime and A prime B double prime. That's its definition. So if you have AB is greater than A prime B prime, that means that there exists, remember that backwards E symbol, kind of drew it bad. That symbol is there exists. So what does this, I should put an arrow. These two are logically equivalent. It's a definition. The definition of AB is greater than A prime B prime is that there exists some point B double prime such that AB is congruent to A prime B double prime and that B double prime is on this side of B prime. You see how that makes sense for this is greater than this segment?
Yeah.
Okay, now let's do less than. So for AB less than A prime B double B prime, you can almost guess exactly how this is going to go. We have A, B, A prime, B double prime, B prime, and its definition is just like this, we just changed the order here. So what does this mean? It means that there exists some point B double prime such that AB is congruent to A prime B double prime and A prime B double prime B prime. Right? This time the point that it's congruent to is between these two. So AB smaller than A prime B prime. Because when I draw that segment down, when I bring that segment down, it's now between here. Does that make sense?
Yeah.
Okay. It's important to understand exactly what these definitions are giving you. In other words, when you know that AB is greater than A prime B prime, you don't automatically know that A prime B prime is greater than AB. Or sorry, is less than AB. Just because you know this doesn't necessarily mean you know this. You're tempted to think that because you know how numbers work, but you don't get that for free. Let me close that one down. So when you're doing proofs using this definition, you need to be careful to use it exactly how the definition says you can use it. Good? Now we'll prove that this is logically equivalent to this. It's a very natural thing to want to do. But you don't have it for free. So do you understand these two definitions?
Yeah.
Any questions about them? All right. So before I go into the next theorem almost comes for free from these definitions. We just need to handle one more case. So if I have AB how can I say this? So if I have A, B, and I have A prime, B prime, and I draw B double prime down here, so that A prime B double prime is congruent to AB, one of three cases happens. Either B double prime ends up here, B double prime ends up here, or it lands right on the point. Right? So we get a theorem, I think it's theorem 4.1. Theorem 4.1. So we get a theorem right out the door after this definition, and the theorem basically states that if I have the segment AB and A prime B prime, then either, or then only one of the following is true. Maybe I'll say it that way. So if I have AB and A prime B prime, then either this is the case. Either AB is congruent to A prime B prime, or, so we could have that, we could have AB is less than A prime B prime, and then we could have the third one, AB is greater than A prime B prime. So that's basically what the theorem states, and you can see how it follows right off the bat, right? So if I have AB, draw some point B double prime on the same side of A prime as B prime, and it either has to end up here, or end up here. If it ends up here, you've got less than. If it ends up here, you've got congruent. If it ends up here, you've got greater than. And those are the only three cases. So one of these three has to be true. Does that make sense? So the author almost doesn't prove it. He says, based off the definition, you can see that this is true. He gives a brief discussion before the theorem. Does that make sense? Okay. So now, let's do the proof, which is kind of the heart of this chapter. And it's exactly what I was telling you that you couldn't automatically do. So let's prove that if AB is greater than A prime B prime, then A prime B prime is less than AB.
Where are you reading that?
So we're going to theorem 4.2. I don't know what page it's on.
If AB is greater than A and B prime.
Is that what it says?
Yeah, you said congruence.
Oh, I did?
It says
Sorry.
greater than.
I didn't mean congruent. I'm going to mess up my words today. Alright. So instead of saying it, I'll write out exactly what I'm proving. So this is theorem 4.2. And it is, if AB is greater than A prime B prime, then A prime B prime is less than AB, and then they're going to do, they want it to be an if and only if, right? So if this is true, then this is true, and if this is true, then this is true. And then doing the backwards is basically the same as doing the frontwards, so just going to go through the forward case. We'll go from this to this, but going from this to this is almost the same. All right. So here's how I start this. 1. Let A be on L and A prime B prime on L prime such that AB is greater than A prime B prime. So exactly the information that it gives us, and let's see the picture that I'm talking about so far. So I'm saying we've got A and B on L, and let's see, AB is going to be greater than, so I'll draw my picture accurately. A prime B prime on L prime. Okay? So here's my picture so far, and I've just set up the situation with the first line of my proof, right? So after we set up the situation, first thing we want to do is just start using our definitions. So what definition could I use in here? Well, obviously I need to use this information. AB is greater than A prime B prime. What does it mean for AB to be greater than A prime B prime?
Then there exists B double prime.
Yeah, so since AB is greater than A prime B prime, basically saying, warning, I'm going to use this definition real quick. Then there exists B double prime, or I don't know, do you guys like the double primes or do you prefer more letters?
Double prime is just fine.
Alright, then there exists B double prime on L double prime such that we have AB is congruent to A prime B double prime and A prime B double prime. Yeah. And to see big picture how these go, for you guys that took my discrete math, you understand that this is often useful, but if you're not comfortable doing a lot of proofs, sometimes if you're not sure where to go from here, what's nice is to go right out the last line of your proof and work upwards, right? So let's try this approach. Where are we trying to get as our last line? Our last line is going to be something along the lines of, therefore, what? What am I trying to end up with?
A prime B prime is less than AB.
Yeah, so you want A prime B prime is less than AB. But what does that mean? Let's unravel that definition and write it up here. What does it mean for A prime B prime to be less than AB? Then there exists, I don't know, I'll call it a C since it's going to be on that line up there and we can't use primes anymore. Then there exists C on L such that A prime B prime is congruent to C, or AC, sorry, AC and ACB, right? So, in order for this to be true, we need to somehow get a C right here. That's the crux of the proof. We need to somehow get a C right there so that AC is congruent to A prime B prime, and that C is in between A and B. Right?
Right.
So that's kind of the crux of the proof. How can we get that C there?
We have the existence postulate of, is it 3, 1? The one that gives us that one.
Oh, yes. So going back to our first postulate, it says, look, if I have this segment here, then there exists one point on this side of A such that this is congruent to this, right? So I could say 3, let C on L such that AC is congruent to A prime B prime. And how do I specify that C is on this side of the line? Here's how I'll say it. And either we have ACB or ABC, right? So C is either over here or over here. These are my two possible scenarios for C.
Don't we have to prove that it can't be B either?
Let's see, why can we throw B right out the window? So if C were on B,
So
I don't see any reason we can
what's
throw
the
it right
first
out
postulate?
the window. Well, yeah, we can. So maybe that's a good point. Then either C equals B, or we have, I'll write my bad cases first, A, B, C, or A, C, B. So we have one of these three cases. Good catch. So we have one of these three cases, right? And that just made me realize I didn't talk about the distinction between equals and equivalence. So, hate to pause in the middle of this proof, but it's an important point. So we'll recap the proof after I talk about this point. Keep saying equivalence, I mean congruent. Equals and congruent are not the same thing. What do I mean when I say that the segment AB is equal to the segment CD? What does that mean?
Those are the same points.
That means A and C are the exact same points, and B and D are the exact same points. Whereas congruent is a much different idea. Right? Congruent just means it satisfies the three postulates of congruence. But equals means we're talking about the exact same thing. That's what equals means. So, when I say C equals B, I mean they're the exact same point. And I've already used equals in this way before, but now the author finally introduced equals in his discussion in chapter 4. And he takes the time to clarify the difference between what congruence means and what equals means. Two segments are congruent, that means they satisfy the axioms of congruence. If two segments are equal, that means we're talking about the exact same segment. Okay? All right. So let's go back to our proof and let's see what we've got so far. So we're saying if AB is greater than A prime B prime, then A prime B prime is less than AB. So we're proving, sometimes you'll see proofs, they'll use like the forward arrow. Say we're proving that this implies this, is the way we're doing it right now. So we're just gathering the information from what we're starting with. We're supposed to start with AB greater than A prime B prime. What does that mean for AB to be greater than A prime B prime? That means A and B are 2 points on L, and A prime and B prime are 2 points on L prime, such that AB is greater than A prime B prime. So just using our given information. We're supposed to show if this is true, then this is true, right? So just setting up our given information. Then now we're going to use our definition. Since AB is greater than A prime B prime, what does that mean? That means there's this point B double prime on L prime, such that AB is congruent to A prime B double prime, and that B double prime is on this side of B prime, right? So we take AB and we bring it down here. The B double prime contains this B prime. So now we say let C be on L such that A prime B prime is congruent to AC. We knew that we could do that because of postulate 3.1, right?
Can you restate what that is?
Yeah, so recap of our three postulates. Postulate 3.1 says, if I've got some line segment here, and I've got some point on a line over here, I can draw a point on either side of this point, namely here and here, such that this segment's congruent to that, and this segment's congruent to that. Okay? So when I have this segment, I can find a point C on this side of A, such that this segment's congruent to this segment. Right?
Yeah.
well, we won't recover all the postulates, but that's what the first one says. We can review them as needed from here on out. So, but we have no guarantee that this C is in between A and B. C could be in between A and B, C could be on B, C could be on this side of B. All we know is it's on this side of A. That's all we know about C. That's all the postulate guaranteed us. So now we know in our heads this is the truth. It can't be here and it can't be here. So we need to show that the point being here and the point being here lead to a contradiction. Okay? So,
Assume.
yeah. So for, by way of contradiction, let's handle the first case. Assume C equals B. Assume C is equal to B. Then what does that give us? If C and B are really the same point, then A prime B prime is congruent to AC is congruent to AB is congruent to A prime B prime. Or A prime B double prime, right? So we know this is congruent to this, right?
Wait. If C equals B, wouldn't that just prove that AC is greater than A prime B prime? So I'm confused because when you say C equals B, you're moving B over to C.
No. I'm saying, so I have this segment.
Okay.
And I'm saying that there's some point C on this segment such that AC is congruent to this. And I don't know where C is. C could be somewhere over here, C could be on B, C could be somewhere over here. I'm going to say C can't be on B and C can't be over here, therefore it has to be here. Okay?
Okay.
So I'm showing at least to a problem when it's on B. So look, if this is congruent to AC, which is really the same thing as AB, but then we already know that AB is congruent to A prime B double prime. So we have this is congruent to this is congruent to this.
Yeah.
Right?
Which doesn't work.
So I had, well, let's see what I wanted. Oh, I didn't need to go to here. We can get rid of this one. So if A prime B prime is congruent to AC is congruent to AB, and AB is greater than A prime B prime,
That leads to contradiction.
yeah, and AB is greater than A prime B prime. And there's our contradiction. Why is that a contradiction?
Because it doesn't define, or because they aren't congruent.
Theorem 4.1. Theorem 4.1 says, look, if you have two segments, either AB is greater than the other segment, AB is congruent to the other segment, or AB is less than the other
So it
segment.
can't be both.
Only one of those three is true. So it can't be two of those three. So we're saying A prime B prime is congruent to AB, and AB is greater than, maybe I should have written it the other way to make this more explicit. Oh shoot, now I forgot what I had. I had AB is congruent to AC is congruent to A prime B prime.
Oh, you're just writing it the other way?
Yeah, so we have AB is congruent to A prime B prime, and AB is greater than A prime B prime. Now I'm still skipping one thing here. Maybe I'm trying to do too much in one line. How do I know that this being congruent to this being congruent to this means that this is congruent to this? The transitive property. So that goes back to our second postulate, which says that congruence is an equivalence relation. So it's reflexive, it's symmetric, and it's transitive. So I should have written that out, but so we know this because Transitive, equivalence is transitive. So we have this and this. Contradiction. Can't be both those. Only one of those can be true. That was our first theorem. Okay? 5. Therefore, C is not equal to B. 6. By way of contradiction, by way of contradiction, assume ABC. Okay? So if C is now on this side, how is that a contradiction? So maybe I'll give you a hint here. So then we know, then we have AB is congruent to A prime B double prime and ABC
Are you saying because it's not congruent anymore?
Let me see. What did I use here? Oh, sorry, that's not what we want to use.
So AB is congruent to A prime B prime.
So we know, yeah, let's think about it. So I know that A prime B prime is congruent to AC, right? What do you think?
If AB is congruent to A prime B prime, then BC is congruent to B prime C prime, then AC is congruent to A. I think you're going to use that postulate, right?
I'm going to use the sum postulate, yeah. So what were you saying? So we have
So if the
A prime B prime
first two parts are congruent,
is congruent to, oh, the other congruence I'm using is if, what are the two things I may use? Because I almost want to use this one.
so that'd be
Let me see what I wrote here. If ABC,
that's just the order.
then there exists D on L,
Okay, yeah, that makes
such that, oh, that's what I did. Okay, I continued this. Now I see what I did. So let me continue it. I'm going to call that point D, and then I'll explain what I'm doing.
AB is congruent to A prime B double prime.
Yeah, such that CD is.
CD is congruent to what?
So here's what I'm going to say. By way of contradiction, assume ABC. Then, by, erase these bottom lines. Then by 3-1 again. Same one we used up here. By 3-1. So maybe I'll take a big picture of what I'm going to do and then I'll get through it. So look, we know that A prime B prime is congruent to AC, right? So what I'm going to do is I'm going to say, all right, then I can put a D over here so that this is congruent to this. So if this is congruent to this, and this is congruent to this, then I'm going to use our third postulate to say that this is congruent to this. So we'll have this is congruent to this is congruent to this, and there's my contradiction. Because I know that these 2 points aren't the same. And I know that there's only 1 point on this side, such that this is congruent to it.
I'm confused to where D came from.
Okay, here's big picture what I'm doing. So right now we're handling the case where this is our picture, right? Get rid of that point.
Okay?
Here's the case that we're handling. So by way of contradiction, assume that C is containing B, basically, between A, right?
Yeah.
And remember, C is a point so that this is congruent to this. So here's what I'm going to do. I'm going to say, look, we know that AC is congruent to A prime, B prime. This is congruent to this. And then I'm going to construct D so that I'm going to make CD congruent to B prime, B double prime.
You have to say such that ACD in that construction.
Yeah.
Instead of ABC.
Or BCD, doesn't matter which way. Just make sure we know it's on that side. So I've got this, this congruent to this, right?
Mm-hmm.
And I've got this congruent to this.
Mm-hmm.
So then by 3, 3, 1, the first one of those, if you look on your list of postulates, the one that says equals added to equals or equals,
Yeah.
3, 3,
A, whatever the book uses, I know that what's this plus this? AD is congruent to, what's this plus this? A prime, B double prime. Right? So if this is congruent to this, and this is congruent to this, then the whole thing is congruent to the whole thing. That's what that postulate said, right?
Okay, I'm lost to where did we find that AC is congruent to A prime, B prime?
We're proving that's impossible. We're doing a proof by contradiction.
Oh, that's been throwing me off the whole time.
We're showing that this is an impossible picture.
Yep.
We're not proving that this is true. We're showing it can't be true.
Okay.
So we're assuming that AC is congruent to A prime, B prime,
Okay.
where it's on this side of B. So assume that that is congruent to that. Make D so that that's congruent to that. Then this whole thing is congruent to this whole thing. Right?
Yeah.
But we already know this whole thing is congruent to AB. Right?
Yeah.
And we already know that B is not equal to D. Right? Because
C is not equal to D, or C is not equal to B.
Well,
we have ABC.
Oh.
Here's where it is. We have ABC. Going clear back to our first between us postulate, it says if you have A, B, C, in other words, if you have B between A and C, then A, B, and C are 3 distinct collinear points. That was our first between us postulate. So if I have A, B, C, then B and C cannot be the same point. So I would have this is congruent to this is congruent to this, and A, B, C. So since I have this and this, I know B is not equal to D, yet B is equal to D. You see my contradiction in my overall thinking?
Yeah.
All right, so let's write it out now. So that's where I'm going with this. So by way of contradiction, assume A, B, C. Then by axiom 3.1, we can find a point D such that CD is congruent to this and ACD. You with me? Then by that, there exists D on L such that BD is congruent to B prime, B double prime, and ACD or BCD, doesn't matter which one we say. Which one do we want to say?
ACD.
ACD?
Actually, BCD makes it more of a obvious.
Yeah, BCD is probably what we should use. So we know that there exists a point D such that BD is congruent to B prime, B double prime, and D is on the same side of B as C. Good? Okay. Then, what does that give us? So then we have AC is congruent to A prime B prime, and CD is congruent to B prime B double prime. Then that and that gives AD congruent to A prime B double prime by 3, 3A. Something like that.
I think you messed up on the line right above where you're writing.
Right here?
Last. You said BD is congruent to B prime double prime. I think you meant CD.
BD, and I did mean CD, thank you. Did I screw up anywhere else? No, I used CD there.
Yeah.
Oops. Did I confuse anyone there? You understand what we're saying here?
Not exactly.
All right.
I just don't know exactly how you got BCD. Like, it makes sense, but I don't know which theorems and statements used.
Okay, so the theorem for that one would have been, it's a theorem in one of the earlier books, but here's what it says. It says if I have a point on a line, and I think they used O, and P and Q are on the same side of the line, then I either have OPQ or I have OQP.
Oh, okay.
Right? So I know I have to have one of those two situations, but I know that it's BC.
Right.
Well, when we make D, we say let it be BC.
Yeah, I could have.
You can make D on either side.
Well, no, I need D.
For this proof, you need it, but since
Yes.
you're the one making D, you can say
I need D to be on the opposite side. So yeah, I could have said, where do I define D?
that same line that we were working on.
Then there exists D on L such that, and here's another way to read this, and D is on the opposite side of C that B's on. How's that? And then we don't even have to use this theorem really. We can pick it to be on the opposite side of C that B's on. Does that make sense?
Okay.
And then is this okay? This line?
Yeah.
Alright. So now we have AD congruent to A prime B double prime. Right? So then AD is not equal to AB since BCD and AB and AD is congruent to AB. Contradiction.
What were you saying on the very last part?
Right here?
Yeah. So they're not equal because they're congruent.
They're not congruent. No, they're not equal because B and D are not the same point,
Okay, I get that, but why did you say and?
and they're not, and they're congruent. Right here, okay, so maybe you want,
Why are they congruent?
that is congruent to that, sorry, maybe I should have written AB.
A prime B double prime is congruent to AB. Okay, there we go.
Yeah. You good with that?
Yeah.
Sorry, I skipped through these steps
So
probably.
that's two things that assume that they're the same point.
Yeah, so right here, Well, no, I can't say that. Oh, from this, they have to be the same point.
Two things that show that they're different points on the very end, which means they can do the same.
Yeah. So this is requiring them to be the same point. This is requiring them to be different points. Those can't both hold.
So something can be congruent, but hold on. Things that are equal are congruent, but things that are congruent are not equal.
True.
Okay,
Yeah, if we're talking about the same line segment, it's congruent to itself.
got it.
But if we're talking about two congruent line segments, they're not necessarily equal. So everyone good with that? All right, so that was all our proof by contradiction to say 7. Therefore,
Postulate 3-1 or whatever it is.
we have ACB. So we're saying, therefore, this is what our picture looks like. And now we can use the definition directly. Then, since, let's see, what are we trying to prove? A prime B prime is less than AB. We're trying to prove that this is less than this. This is less than this. So since A prime B prime is congruent to AC, and ACB, then A prime B prime is less than AB. That's its definition. Good? Now in this proof, basically what we started with was a point on this line, and we used that to construct a point on this line and showed it had to be here, right? When you prove this the other way, you start with the point on this line and then prove the point on this line has to be where you expect. So it's the same type of thinking to prove this the other way. We just proved it one way, right? We showed this implies this. But showing this implies this is the same type of thinking. Okay? So I'm not going to bother going through it. You okay with that? Theorem 4.3 is a nice easy one. No questions about this? Good? Are you trying to get credit for this class, by the way? To replace trig? We'll need to talk about that. I don't know if I can do that for sure. But I could get you math credit, I'm sure.
I don't think they require math.
Oh.
I don't think it's.
Well, if I'm going to do calculus next year, you're going to take my class, so.
That wasn't a true laugh.
He is. All right. Theorem 4.3. What does theorem 4.3 say? It says if A,
C prime, C prime, and A prime, B prime, C prime, and B is the point on C side of A.
and B on the same side of A as C.
Such that AB is congruent to A prime, B prime.
Okay, so that's real. So we have this, and so we have if this and this, and oh, I guess you have to say it, huh? And be on the same side
C is A.
of C as A or A as C?
C is A.
A as C makes more sense in my head.
Oh, yeah, it does. I wonder why they say
Such that
it. Oh,
AB is congruent to A prime B prime. Then ABC. So let's get a picture of what we're talking about. So we've got ABC, and we've got A prime C prime. So we've got AC is congruent to A prime C prime, and, oh, did I do it backwards? And B prime is between A prime and C prime. And then B, basically B somewhere over here. We don't know where B is. It could be on C, it could be on this side, it could be in between. So all we know is that B is on the same side of A as C. And we know that AB is congruent to A prime B prime, right? Then we're trying to show that B is in between A and C. Well, since AB is congruent to A prime B prime, and let's see, what between us did we have? This one. A prime B prime C prime. What's that the definition of?
Then AB is less than A prime C prime.
Perfect. You see how this information gives us? Yeah. All right. Now, using what we just used, what does that give us? If AB is less than A prime C prime, then we just proved
A prime C prime is greater than A prime C prime.
perfect. A prime C prime is greater than AB. Then what's the definition of that? If A prime C prime is greater than AB,
AB is less than A prime. C
then there exists B
Oh,
prime such that A prime B prime is congruent to AB and ABC. Maybe we'll say B double prime, since we already have a B prime, right? So maybe we won't bother with this. Oh, we were doing B, weren't we? What did I do?
I think you started working on the wrong line.
Yes, sir. So let's see. Since AB, I keep forgetting which way we're trying to prove this. What do we have? We have AC is congruent to A prime C prime, and we have A prime B prime C prime, right? And B is somewhere over here. So we won't use B again, but we know A prime is less than, or AB is less than A prime C prime, so A prime C prime is greater than AB. So there exists B, we'll call it double prime, such that A prime B prime is congruent to A B double prime, and A B double prime C. But then by postulate 3(1), B equals B double prime. In other words, there's only one point on this side of A such that this thing is congruent to going to that point. There's not two. So B prime and B B double prime and B are both on the same side of A as C, right? We know B double prime is on the same side of A as C from this, and we know that B is on the same side of A as C from our assumption. So they have to be the same point. Because there's only one point on this side of A such that AB is congruent to A prime B prime. There's not two. Does it make sense why B prime or B double prime and B are the same? I need to stop using B double prime because I keep accidentally saying B prime and that gets confusing. You need to start just using more letters. Does everything in this proof make sense? It's a really simple proof, so if anything doesn't make perfect sense, let's just point it out and make it clear.
Why did you go from 2 to 3? It doesn't seem like what we're saying in 2 has anything to do with 3.
The definition of this is greater than this is there is some point such that.
Yeah, but we already have that one. To be
Oh, whoa! You're right. What did I do?
I think you're still working on this wrong one.
Holy cow. Okay, that was a bad skip. Let's just erase. Let's go all the way back to the right here. If A prime C prime is greater than AB,
Then there exists a point C, maybe. Or there exists a point B prime. But there isn't.
then there exists a point C double prime. Wow, we made a mess out of this. So if this is greater than this, then there exists a point C double prime such that
A prime, C prime.
such that A prime C prime is congruent to A C double prime and A B C double prime. Okay, does that make sense now? I can't believe we screwed that up so bad. All right, let's go over this one more time. It's as simple as proof, and yet we're making a mess. So we know that AB is congruent to A prime B prime, but we don't know where B lands. We know that A prime B prime C prime. So this is congruent to this, and this is between all this. So we know that that is less than that. Okay, AB is less than A prime C prime. Then A prime C prime is greater than AB. That follows. So if this is greater than this, then there has to be some point C double prime over here. We don't know where it is. C double prime, such that A prime C prime is congruent to A C double prime and A B C double prime.
And then we just prove that.
Now we say for then by
Postulate 3-1.
postulate 3-1 C is equal to C double prime. There we go. And then 5, we can just finish off. Therefore, ABC. Proof was as easy as ABC. All right, now does everything make perfect sense? Or do I still have a mistake? Huh? That covers it? All right. Okay, so now we move on to our next definition. And it's a definition that should be perfectly natural. And it's our greater than or equal to, and our less than or equal to. So we got our definition of, let's start with this one. You got through just 2 lines like that. Definition of that, or maybe all right. Definition of A, B, does he do A prime, B prime? Okay. A prime, B prime. So what's the definition of this? This means that AB is congruent to A prime, B prime, or AB is greater than A prime, B prime. And then our definition of AB less than or equal to A prime, B prime is AB congruent to A prime, B prime, or AB less than A prime, B prime. No surprises there. Right?
So all we have to do is prove that it's not the one inequality, and then it's by definition.
Da 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 da. Theorem 4:4. If AB is greater than CD and CD is congruent to EF, then AB is greater than EF. All right, let's go over that one real quick. And that's the last theorem of chapter 4. So, theorem 4:4. What does it say? It says, if AB is greater than CD and CD is congruent to EF, then AB is greater than EF. And writing out the picture and showing you the thinking here is probably going to help make the most sense. So we have AB, CD, EF, right? So, let A, B, C, D, and E, F be segments such that AB is greater than CD, CD, and CD is congruent to EF. All right. So that's our setup. Let's go over big picture what we're going to know. Since AB is greater than CD, I know that there's going to be this point here, call it D prime, such that AD is congruent to this, and D is between A and B, right? Well, if I'm going to call it E because if I put a prime there, I'm going to forget to say prime. I already have an E. What do I have? G. And we'll use G. All right. So since AB is greater than CD, I know that there's this point G, such that AG is congruent to CD and AGB, right? Well, since ES congruent to CD, then ES congruent to AG. So I have ES congruent to AG and ES congruent to AG and AGB, so EF's less than AB, or in other words, AB is greater than EF. So that's big picture what I'm going to do. Follow the thinking? Alright, so since, let's see, what's our given inequality? AB is greater than CD, then there exists G such that AG is congruent to CD and AGB. And what gives us that? That's just the definition of greater than, right? So I'll just use this definition directly. 3. So, since AG is congruent to CD and CD is congruent to EF, then AG is congruent to EF. Pretty verbose. 4. Alright. Since EF is congruent to AG and AGB, then EF is less than AB. Since EF is less than AB, then AB is greater than EF.
Can we just say can we just say 4 like that without any more reasoning? EF is less than AB. How do we know that?
This?
Yeah, it's
This is a definition
a
of it.
reverse engineering the definition.
A definition is not an implication. A definition is they're saying the same thing.
So what's the definition of less than?
Definition of, so which one did we just barely do?
Less.
We did less than. So the definition of EF being less than AB is there's a point between A and B such that EF is congruent to A to that point,
Okay.
right? Namely G.
Right.
So that's a good point to bring up. Make sure you're clear with this. Trying to think up another example off the top of my head that's small. Did you do the algebra review with the plus? Because the way they define subtraction is good. I'll just use one for multiplication real quick, or division. So we say that x equals a over b. What's our definition of that? Our definition of that is, where b is not 0, is that a equals xb. This is the definition of this. You can interchange between those two at will. It doesn't change anything.
Right.
That's what it means to be a definition. They contain the exact same information.
They're logically
That
equivalent.
and that, they're logically equivalent, yes. No better way of saying it than that. It's what definitions do. They give us a short way of saying a lot of information. That's what definitions are useful for. Technically, you could go through all of math and never have a definition.
Right.
You just would have to be really, really verbose about everything that you're proving. This is shorthand for this. Does that make sense? That's all it is. Definitions just help us communicate faster. All right, so that's that proof, and that's the last proof in chapter 4.
Why did they have to define uncensored equal or congruent to do that proof?
For which one?
Just barely. Why did they define that before the theorem instead of after?
Define what?
The less than or congruent to.
Oh, maybe they used it, I don't know.
I don't see it.
When I do these proofs, I try not to look at their proofs in case I do it different and you can read theirs and see it. But you make me want to bring up a point one more time that I brought up a couple times, but my class changes so much as I bring up this point. So just so we're all on the same page, I have never been through this textbook. I've never been through a rigorous geometry course prior to now. So I'm just going through this book and then teaching what I got out of the book. So don't take my word for it on anything. If I make a mistake, correct me, because I'm just like reading the theorems, proving them in my notebook real quick, or reading definitions, writing them in my notebook real quick, and then using my notebook to explain to you. So that's all I'm doing. So it's very probable that I could make a mistake here. I wasn't familiar with Hilbert's axioms prior to this class. I mean, I'd heard of them, but I've never actually used them. And all the geometry I'd done prior to this, I used Euclid's. So be aware of that. And correct me as needed. And I might yell at you, but it's only because you deserve it. All right, so that's chapter 4. Moving on to chapter 5. And chapter 5 of this book is really, really weird because it's like the author's trying to tiptoe around analysis without actually getting into it. And I guess one of you has had calculus, and so maybe the analysis concepts in here will ring a bell outside of that. Chapter 5 is really touching a topic that you get into at the beginning of calculus. And so the author, he kind of, my teacher, when I was learning this stuff, they call it hand-waving. He has hand-waving arguments where he just kind of says, and you can see, da-da-da-da-da, but he doesn't really explain it. It's because he can't really explain it without getting into stuff that's not really the topic of this class. Okay? So chapter 5 is really an analysis topic, talking about the real numbers and properties on the real numbers that we're just going to kind of use. Well, one of them is a property on the real numbers, the other one's the natural numbers, but if it's on the natural numbers, it's on the real, so I guess that's true. So now let's talk about numbers, and what we're going to be using numbers for is length. So the author said you can kind of think about congruence as length. We're going to we're going to talk about length, and then we're going to show congruent and length are really the same thing. So now when you talk about the length of something, you're typically talking about, well, I was about to say you're talking about how long something is, right? That's what you mean by length. So rather than just saying weird tautologies, let's talk about something. If I say that I am, you ask me how tall I am, and I say I'm 69. Does that give you any information? No. What are we missing there?
The unit.
The units. That's what we're missing. The units. So when we're talking about length, we're talking about a number with a unit. That's how we talk about length, right? We say that I am 6 feet tall. And that's how we talk about height. Not really 6 feet tall, as you could probably imagine. But that's the way that we talk about the lengths of things. We need the units. And so in geometry, in this class, what's going to happen is we're going to have some line segment. We're going to want to talk about how long is this line segment. We need to do it in terms of other line segments. Here's my unit line segment for talking about this. This is 6 of those things. And if that thing we want to call 1 foot, and this is 6 of those 1 foot things, then this is 6 feet. So when we talk about lengths, we talk about them in terms of another length. We say, let this be the unit, then this is 6 of my units. Okay? So that's the first thing to bring to your mind, is that when we talk about lengths of things, we talk about them in terms of units. A number alone isn't useful. We need a number and the unit, and that gives us the length, right? Whatever. And then so he kind of introduces numbers. So he starts out and he says, look, in basic arithmetic, you were introduced to numbers, and you probably start out by being introduced to the positive integers. 1, 2, 3, etc. Right? And then maybe you came along. So if you were to go ask, I don't know, when do you first do division? Like 2nd grade, 3rd grade? 3rd grade is when you first do division. You go ask some 3rd grader, hey, what's 9 divided by 3? And they say, it's 3, right? And they can do that. And you say, okay, what's 9 divided by 4? They say it doesn't work, right? It doesn't work. It does work. We just come up with a number for it, and we call it 9/4. What's 9 divided by 4? It's just 9/4. That's what it is. Now, crazy people might write it this way, but anyone who's sane understands that that's 1/2. That's not 9/4. So, 9/4. What's 9 divided by 4?
1/2.
So 1/2 if you write the way that stupid people tell you to write these numbers. Right, they can say 2 and a fourth. No, that's 2 times a fourth. What do you mean 2 and a fourth? Here's how you write it. And then if you were to talk to the third grader, they'd say you're cheating. You didn't even do it. You just wrote 9 fourths. You just wrote 9 divided by 4 again. Right? And so we introduce these types of numbers, and we call these numbers rational numbers. Thank you. So these are the positive integers, and then we learned, I even don't like how he introduces these. You know what? Forget the book. I'm going to introduce them. Start out with the natural numbers. Natural numbers, which we use with that set, or which we represent with this. We're going to get into sets, I don't care. Is a set 0 included, 1, 2, 3, etc. Some authors don't include 0 in the natural numbers. Forget them. We're including 0 in the natural numbers. So that's the natural numbers. And now when you introduce subtraction, like we did before, then you can also introduce negative numbers. For those of you that did the algebra review, we defined a number x such that we defined x such that 0 is equal to b plus x, right? And that x we called negative b. Do you remember doing that? So if we define x to be negative b, then, we defined minus in terms of addition, and then we define negative numbers from minus, right? And so that's how you get from the natural numbers to the negatives included, and that's the integer z, which is negative 3, negative 2, negative 1, 0, 1, 2, 3, and I forgot my dots. You do dots here, meaning it goes on forever, and dots here, meaning it goes on forever. And we use a z with the double lines to represent the integers. Okay? And then the rationals is next. The rationals we get from doing division, just like you expect. So the author also says, if we have a equal to bx, where b is not equal to 0, then x is equal to a over b. Right? And here's how we define our rational numbers. And it's an integer over an integer. So all we knew prior to rational numbers were integers. So if we have a and b are integers, where b is not equal to 0, then x is equal to a over b. And this is what introduces integers into our world. Good? Integers. Rationals. So rationals, which we represent like that, right? Something like that, is all the fractions
Just do it in terms of A and B.
Yeah, I was going to introduce that, but that's new notation. I was going to say it's a over b such that b is not equal to 0 and a and b are integers. So, boom, going to give you a lot more dense notation.
Are there infinite irrational numbers between each set of integers?
Yes,
Holy crap.
and that should be pretty obvious to you. For example, between 0 and 1, what do we have? We have 1. Go a halfway, which gives you a half. Go another half, gives you 3/4. Go another half, gives you 7/8. Go another half, gives you 15/16.
Irrational.
Oh, irrational. Sorry, I heard rational.
I guess you could just multiply pi by different
But yes,
rational numbers.
it's also true with irrational numbers, but we didn't get to do irrational yet. All right, so we got all the way to the rationals. Now, you, just like the third grader, you remember when we were talking to the third grader, and I asked the third grader, what's 9 divided by 4? He said, no, that doesn't work, right? Now we get to you, and I say, what's the square root of 9? You say, oh, I know that, it's 3, it's 3. I say, okay, what's the square root of 2? Say, you can't do that. I say, yes, I can. Guess what it is? It's the square root of 2. You say, you're cheating. You didn't do anything. You just rewrote it. No, that's the number. The square root of 2. It's a perfectly fine number, just like this is a perfectly fine number. Just like this isn't cheating when we're talking to a third grader, this isn't cheating when we're talking to you. Okay? And the square root of 2, it turns out, can't be represented as a fraction. So it's not rational, so we call it irrational. So there's these other numbers which can't be represented this way, but are useful to us. And so that gets us to, we need a bigger set to capture all the numbers that we want, and that introduces the real numbers. And we use the real numbers, this is the symbol we use for the real numbers. And the real numbers are basically any number that you can think of, except for complex numbers if you know what those are. If you don't know what complex numbers are, then whenever I say the word number, you were thinking of a real number. Okay? Now, are you all comfortable with what a decimal number is? So, a real number is any number that can be represented as a decimal using infinite decimal places. So you might say, what about 1? How do I represent 1 with infinite decimal places? Well, that's easy. 1.0, like that. You all okay with what this symbol means? Okay? And so it's a rational number. If there's ever a repeating pattern in the decimals over and over again, it's a rational number. This is rational because it has zeros repeating over and over again. But if it has any pattern in the decimal points repeating over and over again, it's rational, meaning we can rewrite it as a fraction. And if it doesn't have any repeating pattern, then it's irrational. Like the square root of 2 doesn't have any repeating pattern. So maybe I'll show you real quick that if there's any repeating pattern, then it can be represented as a fraction. I won't do the actual proof because there's a lot of subscripts when you do it, and I don't want confusion in the subscripts, but I'll give you the idea of it. So, write out the idea up here real quick. Give me any number.
5.
Sure. How about 52 point? Give me some digits and then tell me when you want me to start repeating them.
39764. Repeat.
39764. Repeat. So let's prove that this is a rational number. Okay? Here's big picture how you do it. Maybe we should start with a smaller one, then go to that one.
Yeah.
We'll start with a cool little proof that some people like. So the proof is that 0.9 repeating is equal to 1. It's not really close to 1, it's equal to 1. How do we prove this? Okay? So let's prove it real quick. So we say, let x equal 0.9 repeating. Okay? Then 10x is equal to 9.9 repeating, right? Then subtract x from that, which is subtracting 0.9 from that. And we get 9x is equal to 9. We get x is equal to 1. Okay? The similar idea of like shifting this thing and then subtracting is exactly what we're going to do over here. We're going to shift this thing, this many decimal places, 1, 2, 3, 4, 5, and then subtract away this thing from it. Okay? So say x equals this thing. Then we've got 1, 2, 3, let's see, 1, 2, 3, 4, 5, x is equal to 5, 2, 3, 9, 7, 6, 4.39764 repeating, right? And we've got that x is equal to 52.39764 repeating, right? So we're going to subtract, and over here we get 99999x is equal to 5239712, and those cancel out. All that cancels out with all that. 4 minus 2 is 2. 6 minus 5 is 1. 7 minus 0 is 7. You see? Mm-hmm. And then what is this? 100,000 minus 1 is 99,999. And lo and behold, x is equal to 5239712 over 99999. Okay? So there's an example of how you could do it with any repeating decimals. You could prove this in general. You just have to use a lot of subscripts and keep track of them. I don't want to confuse you with that. But you see the main idea here now? You see how you could take any repeating decimal and turn it into a rational number? Okay, so the real numbers is a set of all numbers with infinitely many decimal places. Let me use infinitely many decimal places, take all the possible numbers I could write, and that gives me the real numbers. Does that make sense? And then if they have any repeating patterns in them, then they're rational. If they don't have any repeating patterns, then they're irrational. Okay? All right. So that's introducing the basic ideas that he does in the first couple sections. And now he gives some quick definitions and some quick theorems that we're just going to use. We're not going to take the time to prove them all. So now we're going to define what we mean by less than and greater than in the context of numbers, right?
So he just introduced numbers, so we finally get to deal with.
Well, be careful. We get to introduce numbers in terms of line segments.
So
It's not the same as introducing a coordinate plane. Okay? So those are two different ideas. So this might not be giving you as much as you think it's giving you to begin with. It's just going to make so that we can say this segment is 6 times as long as this segment. It's going to make it so that we can say stuff like that. That's what numbers are going to let us do. It's not going to give us like the distance formula that you use in algebra. Okay. So let's see, does he give a definition?
he just there's a lot of exercises.
Okay, so when we're talking about numbers and we say that x is less than y, what's our definition of that? That means that, x is greater than y. That means that x minus y is greater than, x minus y is positive is what he says. Which, okay, I don't like that. How did he introduce it in the exercises? Yeah, because this is assuming positive numbers, and he didn't define positive numbers. This is why I don't really like this section. He's kind of going in a roundabout way of doing stuff. How did he introduce it in the other one? It says if A, B, and C are real numbers and A equals B plus C, oh, there we go. So I don't like him using that definition there, but he gave a way better one in the algebra review. He says if A is equal to B plus C, oh, and C is positive, so I guess either way you have positive and negative numbers. Shoot. So we have to assume you know what positive and negative numbers are to define greater than or less than.
Well, don't know what negative numbers, it's just the subtraction of.
Yeah, so you start out with the natural numbers. What are the negatives of those? They're the additive inverses of those. So yeah, you could define it that way. And then we could define all the positive rational numbers as all the rational numbers whose numerator and denominator are only natural numbers. Right? And then all their additive inverses would be the negative numbers. And yeah, you could define them that way, and that's not a bad way to do it. But I don't think that's the way he does it. I'm trying to figure out where he gives what positive and negative numbers are, and I think he just expects you to know them. So this is why I'm not a huge fan of this section. So what does it mean for A to be greater than B? That means that A minus B is positive. What does it mean for A to be less than B? That means that A minus B is negative. What does it mean for A to be equal to B? No, we don't define equals in terms of minus. Absolutely not. It means they're the same number. We don't define equals.
But it still means that.
Well, if this is true,
Still,
this happens to also be true. But we use what equals is to define negative numbers, not the other way around. Right? We used equals way back in our first algebra review. I don't know how you do algebra without equals. Okay, so let's go over all the other properties he says about less than and greater than. We're not going to bother with proving any of these. We're just going to let you assume that you already know. So if x is greater than y and y is equal to z, then x is greater than z. Any shock there? Is that surprising? If x is greater than y and y is greater than z, then what are we going to write? X is greater than z. So that one was surprising, I guess. X is a positive number if and only if x is greater than 0. X is a negative number if and only if x is less than 0. That makes perfect sense. If x is greater than y, then x minus y is greater than 0, because that means it's positive. And conversely, that's fine.
wait, so 0 is neither.
Huh?
0 is neither then. Positive or negative.
That's correct. 0 is not positive or negative.
So in all our cases, we have to handle 0. In case you realize that positive and negative.
Well, if you get 0, then they're not greater than or less than. They're equal.
Okay, but you have to just take them.
You can go ahead and assume all your algebra knowledge for these relations with numbers. Okay, we know what these are. Measurement. We've already talked about measurement. So let's get to Archimedes. So, introduce measurement one more time, and then we'll get to the Archimedean principle. So once again, when we measure things, what do? We're trying to measure my height. We're doing it in terms of meters, I guess. I'm 1 meter and not quite 2 meters. So that doesn't quite work. So then what do? We use smaller units to get a more accurate measurement, right?
Yeah.
So instead of meters, we might go to centimeters. And if centimeters doesn't quite line up, then we can go to millimeters, etc. And smaller units, right? So that's the idea of measuring. So if I've got this segment, A, B, and I've got this segment down here, A prime, B prime. What do I mean by measuring this? I mean, first put a point here, call it A1, so that this is congruent to this, right? And then stack on another point here, A2, so that this is also congruent to this. And then stack on another point here, A3, so that that's also congruent, and A4, so that that's also congruent, and then A5, so that that's also congruent, and we keep going until we either land perfectly on B, or we go past B, right? And if we get past B, we say, uh-oh, we need smaller units to finish the measurement. Do you see what I'm saying?
Yeah.
Okay. So that's the idea of measuring. And to help us measure, so that we can do this kind of thing, we need what's called the Archimedean Principle. Now, the way that this typically shows up in math is stated like this. For any integer m, or for any natural number m, any natural number you pick, so for all, that means for all m in n, for any natural number you can think of, there exists some other natural number n such that n is greater than or equal to n. In short, any natural number you can think of, I can think of a bigger one. Here's how it's typically introduced. Now we're going to introduce it for our geometry. We're going to give a logically equivalent one that's kind of contrived for our exact situation. So here's what the Archimedean Principle means for our situation. It means if I have some a prime b prime and some ab, maybe erase some of those. So if I have some ab and some a prime b prime, then I can go a0, I can put points on here, a0, a1, a2, a3, a4, all the way up to an. Maybe erase that. All the way up to an, such that each one of these segments is congruent to this segment, and an, and we either have, so if this is an, this one's going to be an minus 1. Everyone okay with those subscripts? So if this is a6, this is a5. If this is a74, this is a73. So the Archimedean Principle says, so I've got some segment AB and some segment A prime B prime. I can sit here, call the first point, call A0. I can go A0, A1, A2, A3, all the way up to AN, such that AN is either equal to B, or I have, so I either have AN is equal to B, or AN minus 1, B, AN. It's between AN minus 1 and AN. Okay? Another way we can think about this is, no matter how far a point away from me you want, and no matter how small a segment you tell me I have to take, no matter how small steps you tell me I have to take, I can eventually take enough steps to reach where you are, or to get past that point. So the line builder postulate that we had before, remember the line builder postulate? It says if I have 2 points like that, then I'm guaranteed a point here and a point over here, right? But the problem with this postulate is it can never guarantee me a certain amount of distance. I can say that postulate never guarantees me a point here. Never guarantees me that I can cover any distance, because I could keep adding infinitely many of these points and never get past a certain point, right? Because if I go half the way there, then half of that, then half of that, then half of that, then half of that, half of that, half of that, half of that, I never actually reach this point. You see that? So now this gives us a guarantee we can go as far as we want down the line. That's what it's giving us. So now there's no point too far that we can't get past it, and we can't be guaranteed some point past it. You see how that's helpful, how that's useful?
Yeah.
Lets us extend our lines an arbitrary amount of distance, is what it's letting us do. So no matter how far away your point is, I can eventually reach or get past it. No matter how small a segment you give me, I can eventually give enough segments that your point is between 2 points. I basically get these 2 points. Well, this point is the one I really want, right? I get this point that's either past that point or it's equal to that point. That's what it's going to let us do. And now the author talks about how we assign a number to these segments. And he constructs a decimal number as we assign a number to a segment. So let's go back now. We're not talking about this principle anymore. Well, we'll use that principle, but let's go back to a concrete example. So this was A3, this was A4, this was A5, this was A6, right? So now, when we're talking about the length of a segment, and here's how we talk about length. When we're talking about the length of AB, we put the line above it. Here's the number that represents that. The number that represents AB in terms of this unit is 1, 2, 3, 4, 5, and then some, right? So we got 5, and now we need to zoom in on this and then some. So I go and I take my unit, and since we like the decimal system, I break this up into tenths. And now I measure this in terms of tenths, and I repeat. So I say, how many tenths was that? That was 1, 2, 3, 4. Okay, so it was 3 and then some. And I could keep getting closer and closer and closer. And eventually I might reach a 0. And then I could put repeating zeros forever, or I could keep getting on closer and closer and closer. Maybe it's an irrational. You see what I'm saying? So that's what we mean by the length. If we were to indefinitely continue this process, then we would be constructing the length of this thing in terms of this unit, whatever our unit is. Do you see what I'm saying? That's what we mean by the length of that thing. It's that number. Now, I'm saying continue this process indefinitely. We don't have a good way of talking about that yet. That's a calculus idea. That's what I mean by this author kind of has to just say, we're going to do this and call it a number. But do you get the idea? So that's what we mean by the length of something. So if you give me some point, if you give me some line segment, I can figure out its length. That's what the Archimedean Principle lets me do. It says, if you give me AB, I know how to find the length of AB in terms of some units. Okay? Very, very important. This is a segment. This is a number. Segment, number.
Okay.
When we're talking about the length, we're talking about the number. Good? Okay. So, that tells us we can go from a segment, from a segment to a length. Now we want to do it the other way. Can you give me any length, any number, and I construct AB such that the length of AB equals that number? So in other words, I can find a number for every length. Is it possible that I can construct a line segment of a particular length for any number you give me? Do you see this, the second way we think about this? In other words, are all my lengths just by chance, for some reason, going to be integer numbers? No, that should be pretty obvious. Are they all going to be rational numbers? So you're telling me it's possible to draw a length so it has an irrational value? I'll give you one real quick. Let's call that length 1. You with me? You don't know how to do this yet, but we'll learn how to construct a square with it. And I can construct a square so all those lengths are length 1. Right? And then I construct that. What's the length of that? Square root of 2, which is irrational. So we know that we can get at least that irrational number. But the question is, for any number you can think of, is it possible to construct a line segment of that exact length? Right now we don't have the tools to prove it. And in fact, there aren't tools to prove it. It's our next postulate. So we got the Archimedean Principle, and then the next one is called the Completeness Axiom. And the Completeness Axiom, in short, says there's no holes in our lines. For any number you can think of, you can draw a line segment of that length on it. You can find a point that goes from where a line segment starts to there. Let me try this again. If I have a line and a point A, for any x you can think of, I can draw a B such that the length of AB is equal to x. Is that a fair way to say that? That's what I mean by the completeness axiom. Because if there were some x that I can't make an AB for, then it's like there's a hole there, right? There's no such thing as a point at right there. So this completeness axiom is giving us that our line is very dense, in a sense. There's no holes. There's no gaps. Using some of your calculus terms, it's continuous. Okay? So we can't prove it. It's an axiom. Something we just assume. And in short, it basically says that we can model the points on this thing with real numbers is what it's coming down to. You good? So chapter 5, 2 more postulates are introduced. The Archimedean Principle, which says in short, for any number you pick, I can pick a bigger number. In terms of our line, it says for any point you pick, I can eventually find a point past that using whatever unit you want. Then I can keep adding on congruent segments to get past that. Archimedean principle. So that tells us, because this is how we measure, that tells us any line segment you give me, I can measure it. The second one, the completeness axiom, says any measurement you give me, I can find a line segment that has that as its measurement. You good with those two ideas? So those are the two big ideas of chapter 5. And they're not really geometry ideas, they're more analysis ideas. There's some theorems that he proves in there, and once again, I don't really like his proofs of the theorems. But what his theorems say are, if AB is congruent to A prime B prime, then AB's length is equal to the length of A prime B prime. And conversely. Does that make sense? It should make sense, because what we were kind of aiming at with congruence was something that meant the same length. And so now we have a way of talking about the length of something, and that is logically equivalent to their congruent. Their congruent means they're the same length. They're the same length means they're congruent. You can use those definitions interchangeably. I don't think that there's anything of great value going through the proofs of those. Second part of that, just like you'd expect, and then same thing with lesson as well. Good? And then the very last thing is his change of scale. And he doesn't even prove his theorem. He just states it as a theorem. I don't know why he doesn't state it as a postulate if he's not going to prove it.
He's done that before.
He has? So, let's give the idea of it. If I say that I am exactly 2 meters tall, how many centimeters tall am I? 200. Why 200 centimeters? Because there's 100 centimeters in a meter, right? So basically what he says is, if I have segment AB and it's equal to 3AC, so here's AB, not AC, let's do CD, and here's CD, and I know that, the length of that's equal to 3 the length of those. And I know that the length of CD is equal to 2 times the length of EF. Here's EF. So if I know this is equal to 3 of those and this is equal to 2 of those, then what do I know? Then AB is equal to, its length is equal to what? 6 EFs, right? So if this is 3 of these, and this is 2 of those, and this is 6 of those, it's a change of scale. We change the units that we're using to measure this. Okay? One more important note, as we were talking about coming up with the lengths of the number, we were taking our units and dividing them into units of 10, into 10 equal intervals. Technically, in our geometry, we don't know how to do that right now. That is something we will be able to do in our geometry. It just requires us to have parallel lines, which we haven't talked about yet. So he brings them in and he says, we're going to prove that what we're doing is legal later, but here's what we can do. Does that make sense? So if that part of what I said confused you, good, it should have. You should have been wondering, how can we do that? We can't yet. So the author puts a note in there that says, you'll be able to do this later, but we need it now, so we're going to use it. Something to that effect. So that is the end of chapter 5. And then chapter 6 is when we get to finally start geometry that you probably envisioned when I said, let's do geometry. We got to start talking about triangles and properties of triangles and proving things with triangles. I feel like there was one more thing I was going to show you guys if we had time.
Do we even know what a circle is yet?
No, we have no definition of a circle.
Just triangle.
We have a definition of a triangle and definition of a line, not a definition of a line, I meant a line segment. Where did I do that? Shoot. Well, you won't bother trying to find it. I had the little proof. I did it real quick. I don't want to take the time to do it now in case we get screwed up. But you remember how in the last group of postulates, the one where it said equals added to equals or equals, and equals subtracted from equals or equals, and I had a star next to the subtracted one. And I said this can be proof from the other ones. I had that proof real quick, but lost it somehow. Okay, so we'll call it good for there with covering new material. For homework,